And we're back. Welcome back and happy Tuesday. Today we're going to continue on with some distributions that are continuous distributions, and we'll prove a few properties about them concerning the expectation and the variance, as well as some tools from calculus that we need in order to do so. But before we begin, some administrative bits. By the 12th of November this month, please make sure you get through the reading, sections 4.1 through 4.2.4, pages 75 through 92. In addition, make sure you're reviewing integration by parts. There's the link from Khan Academy. It's a fantastic module. And also, please make sure that you review the indefinite as well as the definite integral. And so I'm going to hold all of you responsible for this. And moreover, it's something you should know from the prerequisites for this course. Okay, so why don't we begin? Before where we left off, we talked about the summary statistics of the continuous distributions. And we said the continuous distributions traffic in real valued quantities. Specifically, when we look at the things like expectation, variance, and covariance, we use the integral instead of the summation. And the integral is because we have a density function, and this is how we put together a number of these terms when we traffic in continuous distributions or real valued random variables. Okay. So please make sure you're reviewing example 4.2 in the book. So let's take a look at the uniform distribution. And so the uniform distribution is very important to modeling stochastic systems. It refers to probabilistic outcomes that are equally likely. And so, of course, we said this is random. And so random number generators and things like samplers often use the uniform distribution. It's very important to probability. And so the density function for the uniform distribution, if we were to write out x is our random variable, here's our random variable, it's distributed as, that's what the little squiggle tilde means, is distributed as a uniform distribution, equiprobable, and its uniform distribution, or this uniform distribution, is parameterized by two parameters, a and b. A is the low point over which this uniform distribution is defined, and B is the high point over which this uniform distribution is defined. Okay, so the density function is f of x is equal to 1 upon b minus a. And so for every value of x for the uniform distribution, between x equals values a and b, it's 1 over b minus a. Everywhere else, it's 0. And so if we were going to plot the uniform distribution, here along the horizontal axis, we have our random variable x, and it can take on values little x. And we mark point A along this horizontal axis and B. And then we have a probability P of x along the vertical axis. And so if we look at this point is the value 1 over b minus a, that's a probability, and our distribution, our uniform distribution, everywhere between a and b, it's going to be a probability of 1 upon b minus a, and everywhere else it's going to be 0. And so here we'll draw all those points to the left or less than a, it's going to be 0, here's 0, and everywhere to the right of b it's going to be 0. But everywhere between a and b, inclusive of the endpoints, it's 1 upon b minus a. So all of the values along the real number line here, between a and b, they're equiprobable at a probability of 1 upon b minus a. And that's our uniform distribution. You cannot have the following uniform between minus infinity and plus infinity. It does not exist. The reason being that is if it has infinite width, 1 over b minus a is 1 over infinity, where the density function then is always 0 everywhere, and it doesn't work. Okay, And so the uniform distribution is defined between finite intervals, and all of the values, uncountably infinitely many between A and B, are equiprobable. Okay. And so I'm going to leave this up to you to look up, but given our density function, f of x is 1 upon b minus a, the expectation of a uniform distribution is a plus b divided by 2. The variance is b minus a quantity squared divided by 12. And I'll leave this to you to look up. Please make sure you do so. We will be using that in the future, in the near future. All right. And now when you do this, remember to go back to first principles for what expectation means. And in the case of this continuous distribution, we're going to use the integral. And so in this case, e of x is going to equal to the integral from minus infinity to plus infinity, remembering that if it's less than a, the probability is 0. If it's greater than b, probability is 0. Everywhere between a and b, it's going to be non-zero. And so as an expectation, we say x times p of x dx, where this p of x is our density function. Likewise, the variance, we say variance of x is equal to integral of x minus its expectation, quantity squared, times p of x dx. And again, we use the integral. So I'll leave this to you to look up. All right. So let's take a look at the exponential distribution, and this is where we'll spend most of our time today. And so we talked about the Poisson distribution, and we talked about this idea called a rate, and the rate was the average number of observations in each so-called module of observation, delta t. And we said that this delta t, the only requirement for this Poisson configuration, was that it had to be the same everywhere, throughout every module proceeding in time. We gave the mass function to Poisson, p of x, is equal to e to the minus lambda times lambda to the x upon x factorial. And we call this a probability mass function because the Poisson traffics in the number of events that we observe, and this number of events is countable. Therefore, it's a mass function. And we proved that the expectation of a Poisson variable, mu, is equal to lambda, the rate, and the variance, sigma squared, of the Poisson random variable is also equal to the rate lambda. And so the Poisson's mean and variance are the same. That's what we found, and we proved it. And last time we also saw the relationship between the binomial distribution and the Poisson. The Poisson is basically a binomial distribution with a large sample limit. We took the limit as n goes to infinity. All right, so let's move forward. Now, when we talk about events in time, one of the things we can think about is this idea of a so-called rare event. What does rare event mean? What does it mean when we say an event is rare? Well, going back to the Poisson configuration, rare event means that we're not going to have too many of these occurrences, these dots, within each window of observation. So therefore, when we refer to a rare event, we mean it does not happen very often. The rate is relatively small. And so how do we mathematically express does not happen often? We say a rate is very small. So for a relatively small rate, that corresponds to these events not happening very often. Now, of course, if an event doesn't happen very often, one of the natural questions you might want to ask, well, if our Poisson tells us the number of events that occur in each window of observations, if it's relatively rare, one of the things we might enterprise to know is the amount of time between one occurrence of the event and the next occurrence of an event. So another important quantity is the length of time. So another important quantity is the length of time between events. And I marked this here on the Poisson configuration as this green arrow here. So here we have the first event. Here's an event, occurrence. We have another occurrence of an event. And this green arrow is the amount of time that transpires between that first occurrence and that next occurrence. And so what this idea of the amount of time between events, it answers the question of how long one has to wait before the next observation occurs. All right. And so this idea of that rare event and the amount of time until the next observation, or the time between events, that's called the exponential distribution. And so any random variable describing such a time, certainly time is uncountably infinite, so this is going to be continuous distribution. And we say x is distributed as x for exponential, exp, and it's parameterized by lambda. Now, the density function, again, we call it a density because time is uncountably infinite. And so our probability density function, f of x, for the exponential distribution is lambda times e to the minus lambda x. Now, it almost looks a little bit like a Poisson. If we go back to the Poisson, that's e to the minus lambda, but we have that lambda to the x over x factorial. So we still have an e to the minus lambda here. They are related, but they're not the same. The Poisson is a discrete distribution, traffics in countable quantities, where the exponential is a continuous distribution, traffics in uncountable quantities, namely time. All right, so we have our density function, f of x, for the exponential. F of x is equal to lambda e to the minus lambda x, and our assumption is for all x greater than 0. Because if x is equal to 0, well, that's not a different event, that's the same event. So x is greater than 0. Sometime later, the next occurrence or observation of the event will happen. So let's take a look at the cumulative distribution function. And this cumulative distribution function, big F of x, we said the CDF is just the integral for continuous distribution from minus infinity up to that quantity x. And what we're trying to encode there is the probability that random variable big X takes on a value that's less than equal to little x. Now, of course, we would, for this CDF, we would compute the integral from minus infinity up to x over the density function f of x dx. But then we just said for x greater than 0. And so this density function has a value of 0 when we go from minus infinity to x. So we can break this up into the sum of two integrals from minus infinity to 0, f of x dx, and then we add to that the integral from 0 to x, our density function f of x dx. Now this first term, that's 0. This density function is undefined, takes on a value of 0 for values x less than equal to 0. And so we're just going to look at this integral from 0 to x over this density function to express this cumulative distribution function, or CDF. Okay, so let's do this. So we're going to substitute for our density function. That's lambda e to the minus lambda x power. And we're just going to do this integral. And we're going to do that for x greater than 0. So let's try this out. Let's set up a blank page, and we're going to do the definite integral. And for this definite integral, we're going to take the integral from 0 to x of lambda e to the minus lambda x dx. Now, under this integral, lambda does not involve x anywhere. That's not captured underneath this integral. So this looks like a constant for all intents and purposes. So we're going to factor that out, and we write lambda integral 0 to x e to the minus lambda x dx. And so now we're going to make a u substitution and compute the Jacobian. So we're going to say let u equal minus lambda x. So that means du is equal to minus lambda dx. And if we multiply both sides of equality by minus 1 upon lambda, that's minus 1 upon lambda du is equal to dx. So we're going to make that substitution when we substitute for u. So with that substitution, we have lambda times the integral 0 to x. We have that factor of minus 1 upon lambda, minus 1 upon lambda, and now we write e to the u du. Okay, so e to the u du, the integral is just e to the u, so that's lambda times minus 1 upon lambda times e to the u. So we substitute back in for u. We said let u equal minus lambda x. So this implies lambda times minus 1 upon lambda e to the minus lambda x. And so if we do that, well, that's e to the minus lambda x. So that's our definite integral. Now, of course, we're going to take our minus e to the minus lambda x, minus e to the minus lambda x, and we're going to evaluate it at the 0 point, and we're going to subtract that from the evaluation at the x point. Okay, so that's equal to, we're going to say at x, it's going to be, for x, minus e to the minus lambda x, okay, and we're going to subtract from that the evaluation of the integral at the 0 point. So I'll just label it the 0 point. So that's e to the minus lambda times 0. That's e to the 0 minus e to the 0 power. So that's just going to be minus 1. Okay, so we put it all together. That's minus and minus, that's plus, that's 1 minus e to the minus lambda x. So this is going to be our value for the CDF for the exponential distribution. F of x is equal to 1 minus e to the minus lambda x. And there's our result. And so here we apply this u substitution, take the Jacobian, solve for the integral, the definite integral, and we get this result that the CDF for the exponential distribution is 1 minus e to the minus lambda x. Okay, so please make sure you review the definite and the indefinite integral. Khan Academy has a wonderful module on that. All right, so now what we want is the summary statistics. We're going to compute the expectation of this exponential distribution. And to do that expectation, of course, expectation is defined between positive and negative infinity. Now, this e of x is equal to the integral from minus infinity to plus infinity of x. It's the probabilistic weighted average, but we're going to use integration instead of summation because this is a continuous distribution. So x times the probability density function dx. Now, as was the case before, we're going to separate out the value between minus infinity and 0, x times f of x, or density, plus from 0 to positive infinity, x times our f of x, our density. And so we do this because we know that it's 0 whenever x is less than or equal to 0, and it's non-zero whenever x is greater than 0, because that's where this exponential distribution is defined, for time values that are greater than 0. Okay, so now we have our expectation, and we're going to set this up using integration by parts. Make sure you review integration by parts. Khan Academy has a wonderful module on integration by parts. We're going to start out with the product rule for derivatives for calculus. And suppose you have some function, and that function is of the following form: f of x times g of x, the product of two functions of x. Now, if you want to take the derivative of this quantity, dx of f of x times g of x, well, the product rule for differentiation tells us that's just equal to dx of f of x times g of x plus f of x times dx of g of x. Said differently, that's equal to f prime of x times g of x plus f of x times g prime of x. Okay, so now we have an expression for this particular derivative. We say dx of f of x times g of x is equal to f prime of x g of x plus f of x times g prime of x. So that's the product rule. Product rule of differentiation. Differentiation. Okay. And so now let's take this expression and we're going to take the integral of both sides. Because equality is there, if you take the integral of the left-hand side, you also have to take the integral of the right-hand side. So we're going to take the integral of dx of our f of x times g of x dx, and that means we're going to take the integral of the sum. Now, the integral of the sum is the same as the sum of the integrals. So we're going to say the integral of f prime of x g of x dx plus the integral of f of x times g prime of x dx. Okay, so we can do a little bit of simplification now. If you take the integral of the derivative, well, that's just f of x times g of x, okay? And we're left with, on the right-hand side, the integral f prime of x g of x dx plus integral f of x g prime of x dx. So now what we want to do is we're going to subtract off this term from both sides of equality. So we're going to do that subtraction. That's going to give us f of x times g of x is equal minus integral f prime of x g of x dx is equal to the integral of f of x g prime of x dx. So now we're just going to write this right to left instead of left to right. It doesn't matter which side of equality is on the left or the right. So we're going to say integral of f of x times g prime of x dx, that's the right-hand side of equality, is equal to f of x times g of x minus the integral f prime of x g of x dx. So what does this do? This is called integration by parts. And what this does, and it derives from the product rule of differentiation, and it gives us a method that we can use to reduce a complex integration. And so here, if we have an integration of this form on the left-hand side of equality, that's just f of x times g of x minus this integral f prime of x times g of x dx. And so here, if we have this original expression, f of x times g of x, involved in this integral, well, we can simplify it. And how the simplification works is by choosing one term in your expression to be the f of x term and the other to be the g of x term. And if you choose it the right way, your f of x term, well, this f prime of x will simplify. Simplify means the exponent gets smaller until eventually the exponent goes to 0, right? And so This integration by parts is a method for simplifying a form of complex integration in this form on the left-hand side of equality, decomposed as defined on the right-hand side. Choosing f will make it simpler. And so what does this mean when you're solving such a problem? Well, there are 4 different steps. The first step is choose your f of x term. Second is, in this expression, choose your g prime of x term. Third thing you're going to do, calculate f prime of x, okay? And then lastly, calculate your g of x. And your g of x is nothing more than the integral of g prime of x dx. Okay, so if you have an expression, let's say that expression is x times e to the x, well, if you're going to compute the integral of this term, dx, if you choose your x as the f of x term, and this other one, e to the x, as your g of x, that's your f of x, and that's your g of x. Well, when you compute this expression, that x will go to 1, and it'll simplify your definition for that complex integral. Okay, so if you choose your f of x term and your g of x term incorrectly, it won't simplify. Just switch which ones you chose for your f of x and your g of x term. All right, your g prime of x term. So let's take a look at our expectation of the exponential distribution. We said our expectation, e of x, is just a probabilistic weighted sum. We said e of x is equal to the integral from 0 to infinity, and 0 to infinity because our x has to be greater than 0. So it's integral from 0 to infinity of x times the density function f of x. Or you could say p of x if you wanted to. Now, substituting for f of x, we said f of x is equal to lambda e to the minus lambda x. And so we get this expression. And we're going to use integration by parts in order to simplify this expression. So we're going to choose this x term to be our f of x, and we're going to choose this term to be our g prime of x. Okay, so first, step 1, we choose our f of x. So we say f of x is equal to x. Step 2, we're going to choose our g prime of x. G prime of x is equal to lambda e to the minus lambda x. Calculate your f prime of x. F prime of x is equal to 1. And then calculate your lambda e, your g of x. So your g of x is equal to the integral of lambda e to the minus lambda x dx. Now, if we make a u substitution, that just gives us integral of lambda times minus 1 over lambda e to the u du, and that's just equal to minus integral e to the u du, which is just equal to minus e to the u. Substituting back for e to the u, for that u substitution, that's equal to minus e to the minus lambda x. Okay, so if we do that, well, let's do our integration by parts. We said that our integration by parts, our integral 0 to infinity x lambda e to the minus lambda x dx is equal to our f of x times our g of x. So our f of x is just x. Our g of x is minus e to the minus lambda x. So that's minus e to the minus lambda x. So that's our f of x. That's our g of x. Okay, we say minus the integral from 0 to infinity of f prime of x. That's 1. That's our f prime of x. and we multiply that times our g of x, and that's going to be minus e to the minus lambda x. Oops, to the minus lambda x. There we go. So we rewrite this. We say minus x e to the minus lambda x. And now we say, all right, well, we say plus integral 0 to infinity of e to the minus lambda x. Okay, so if we do that, okay, we're going to make a u substitution here. If we make a u substitution, well, we still get that minus x e to the minus lambda x for that first term. And our u substitution, we're going to let u equals minus lambda x. So that's 1 over minus 1 over lambda e to the minus lambda x. Okay, so we have these two terms in our expression. So we have a negative sign here. We have a negative sign here. So we're going to take this expression, minus x e to the minus lambda x minus 1 over lambda e to the minus lambda x, and we're going to substitute for x equals infinity, and we're going to subtract from that the substitution for x equals 0. So let's take a look at what happens. For the infinity case, x equals infinity, well, you have e and minus x e to the minus lambda infinity, right? So this is a negative exponent, so the e to the lambda x is in the denominator. Infinity as an exponent grows bigger than infinity as just x. And so this term is going to go to 0. So it's minus 0 minus, you have 1 over lambda e to the minus lambda x. That's the same as 1 over e to the lambda x. That's infinity, so that's 1 over infinity. That's going to be 0. So that's minus 0 minus 0. And we're going to subtract from that the evaluation for x equals 0. And so for x equals 0, this term is 0. 0 times anything is 0. So that's a minus 0. And then we're going to have minus 0 here, 1 over lambda, times e to the 0 power. That's just 1. So now if we take all of this together, that's 0 minus a minus 1 over lambda. That's just 1 over lambda. Okay. And so that's our result using integration by parts. We take this integral, we simplify it using integration by parts. So there's our result, and we get 1 over lambda for the expectation of an exponential distribution. There's our result. All right, so let's move on. That's our expectation. Let's move on to the variance. Now, for the variance, we're going to make use of the variance equation. And so I thought it'd be helpful to go over the variance equation. And this variance equation derives from the definition of the variance, and it's a simplification to make life easier for you in calculating variance. So here we have, for a continuous distribution, the variance is the integral x minus its expectation quantity squared, because you care about the magnitude, not the direction, times p of x. And p of x, that's our density function. Sometimes they'll say f of x, sometimes they'll say p of x. It's all the same thing. So let's take out this expression. We're going to multiply out this squared term using the FOIL rule. So we have the integral x squared minus x times 2 times x e of x, right, because we have the cross terms, plus e of x quantity squared. All of that is multiplied by our density function, probability density function, p of x. And so now we're going to distribute this p of x inside of that parenthesized expression. That gives us the integral x squared times p of x. That's our first term. So we have a first term, we have a second term here, we have a third term. We'll do the same thing for the second term, minus 2x E of x times the density function P of x plus E of x quantity squared times our density P of x. Okay, so if we do that, well, we make the observation that the integral of the sum of terms, term 1, 2, and 3, and the subtraction is nothing more than a sum, then adding the negative. The integral of the sum is the same as the sum of integrals. So we're going to separate these out into separate terms. So we have the integral x squared times the density P of x minus the integral 2x e of x times our density P of x plus the integral of e of x squared, so e of x quantity squared times our density function P of x. And so now we're going to make some observations. Well, we still have here in our first term here, we have our integral x squared times P of x. And we notice here that this 2 is a constant, and our expectation, e of x, which is also nicknamed mu, that's also a constant. And so we can take out this 2 term, we can take out this e of x term out from underneath this integral. So we say minus 2 e of x, and what is left? The integral x times P of x, okay? And then we also make the observation that this e of x is also constant. A constant squared is just a constant. So we can pull that out from underneath the integration. We write e of x quantity squared integral P of x. All right. So now we're going to do a little bit more reduction here. So we have our integral x squared times P of x minus 2 expectation of x. And if we look at this integration, that's nothing more than e of x. So we have e of x times e of x. Plus, we have e of x quantity squared times that sum of all the probabilities for the density. That's just 1 by law of total probability times 1. So we're left with the following expression. We have our integral x squared times P of x minus 2 e of x quantity squared, because it's e of x times e of x, plus e of x quantity squared. Okay, so if we look at this, we have 2 of these e of x squareds, minus 2 of them, plus 1 of them. That's the same as minus 1 of them. So that's equal to integral x squared times P of x minus e of x quantity squared. Okay, and so if we look at this first term here, that's nothing more than the expectation of x squared. We have the quantity x squared, probabilistic weighted average onto the integral because it is a continuous random variable. So we have e of x squared minus e of x quantity squared. And so we have our result, the variance of any random variable x is equal to the expectation of random variable x squared minus the expectation of random variable x quantity squared. And that's the variance equation. And we're going to use that variance equation to show the variance of our exponential distribution. Okay, so we just got done showing what the expectation was from before, and we use integration by parts to do that. And so we have that result 1 over lambda. So this e of x here is 1 over lambda. If we square it, that's 1 over lambda squared. So we're halfway there, check, in figuring out the variance if we use the variance equation. So what remains is computing this e of x squared. And once we do that, we're going to take that result, subtract from it this 1 over lambda squared, and this is going to give us the variance of the exponential distribution. All right, so essentially, we have the expansion of our e of x squared. There it is. So we have x squared times the density function dx integrated from 0 to infinity. That's just the definition for the expectation for the continuous random variable. It's a probabilistic weighted average of that quantity inside of the bracketed expression. and we're subtracting off e of x, which we showed is 1 over lambda, and e of x is quantity squared, so it's 1 over lambda squared. So now what we're going to do is solve for this first term here, this integral from 0 to infinity of x squared lambda e to the minus lambda x power. All right, and we're going to do so with integration by parts. If we look at this integration by parts, we have an expression for e of x squared for the exponential distribution. And so here is our x squared, and here is our density function, p of x. You could also write f of x dx, integral from 0 to infinity, because time is defined as being greater than 0. Okay, so with this integration by parts, what we're going to do then, we have our integral 0 to infinity, x squared lambda e to the minus lambda x. And so this expression can be expressed in the form of some function f of x times g prime of x. And so we're going to choose which one of these is going to be our f of x and which is going to be our g prime of x. And if we do so and choose the f of x term correctly, we can simplify, because of that definition, the integral, or integration by parts, the integral of f of x times g prime of x dx is equal to f of x times g of x minus the integral of f prime of x times g of x dx. And so it's this f prime of x that gets us to simplify. All right, so here we're going to choose this x squared term as our f of x, and we're going to choose this lambda e to the minus lambda x as our g prime of x. So the first step, we said, is choose your f of x. F of x is equal to x squared. Choose your g prime of x. G prime of x is equal to lambda e to the minus lambda x. Calculate your f prime of x. F prime of x is equal to 2x. Calculate your g of x. G of x is equal to the integral of lambda e to the minus lambda x dx. So we're going to do a u substitution. If we do that u substitution, this gives us the integral lambda times minus 1 upon lambda e to the u du. Now, let's see, these lambdas cancel, so we're left with the integral of minus e to the u du. That's just minus e to the u. Substituting back in for u, that gives us minus e to the minus lambda x. Okay, so there is our g of x. G of x is equal to minus e to the minus lambda x. Okay, so there we have our 4 parts for integration by parts. And so we're going to write this out. We're going to say the integral 0 to infinity of x squared lambda e to the minus lambda x dx is equal to, say, f of x times g of x. So that's x squared times minus e to the minus lambda x, okay, minus our integral f prime of x 2x times g of x. That's times minus e to the minus lambda x, and we have a dx. Okay, so we simplify that a little bit. We have equal to minus x squared e to the minus lambda x minus, that's plus, integral 2x e to the minus lambda x dx. Okay, but we're not done yet. The reason we're not done yet is because, well, this integral, we can simplify that as well. And how we're going to simplify that is by another round of integration by parts. And if we do that other round of integration by parts for this expression, well, if we choose as our f of x, we choose f of x is equal to 2x. We choose g prime of x is equal to e to the minus lambda x. We calculate f prime of x is equal to 2. And you notice how that simplifies. No more exponent for x. And lastly, g of x is equal to the integral of e to the minus lambda x dx, which through a u substitution is minus 1 over lambda e to the minus lambda x. Okay, so now we're going to unpack this second term through another round of integration by parts. So we have the original minus x squared e to the minus lambda x plus we have f of x times g of x. So that's 2x times our g of x is minus 1 over lambda e to the minus lambda x. So that's our f of x times g of x. And we're going to say minus, okay, integral, and we're going to say f prime of x, that's just 2, times g of x dx. So g of x is minus 1 over lambda e to the minus lambda x dx. Okay, so now we're going to simplify this expression here. Let me just rewrite it, clean it up a little bit. Minus x squared e to the minus lambda x plus, that's a minus because of that minus sign, minus 2x over lambda. So 2x in the numerator, lambda in the denominator, leading minus sign, e to the minus lambda x. And that last term, that's a minus and minus with a plus, plus integral of 2 over lambda e to the minus lambda x dx. Okay, so now if we look at this integral here, this integral, we're going to do a u substitution, and if we do a u substitution for that integral, we're left with, well, that constant 2 over lambda, that stays. We're going to multiply that by a negative 1 over lambda, and then we're going to have our e to the minus lambda x. And so if we clean all of this up, that's equal to minus x squared e to the minus lambda x minus 2x over lambda e to the minus lambda x. And that last term we had, that's just plus, that's 2 over lambda, that's minus, so that's a minus 2 over lambda squared e to the minus lambda x. Okay, so we're going to take this expression and we're going to bring it over onto the next page and solve for the integral. So we had from before the integral 0 to infinity of x squared lambda e to the minus lambda x dx, and that was equal to the expression that we got thus far for integration by parts. We had minus x squared e to the minus lambda x minus 2x over lambda e to the minus lambda x minus 2 over lambda squared e to the minus lambda x. And so to compute the integral, all right, we're going to take this expression and we're going to evaluate it at x equals infinity. And we're going to take that expression and we're going to subtract from it the value of this expression for x equals 0. So let's take a look at the case where x equals infinity. So for x equals infinity, we have x squared, we have e to the minus lambda x. That's the same as 1 over e to the lambda x. That is an exponent involving infinity, and that increases faster than a variable that's infinity squared. So this is all going to be 0 because you have something that's big over something that's much bigger because it's e to the x in the denominator. So that's going to be minus 0. And likewise here, we have 2x. Well, x equals infinity, yeah. All right. And you have e to the minus lambda x. That's the same as 1 over e to the lambda x. If x goes to infinity, the denominator increases faster. So that's also going to be minus 0. And likewise, here we have 2 over lambda squared, e to the minus lambda x. That's the same as e to 1 over e to the lambda x power. You have x is infinity. That's going to be 0. So because you have infinity in the denominator, that's minus 0. So we take that, which is all zeros, minus 0, minus 0, minus 0, minus the evaluation of this expression for x equals 0. All right, so x equals 0. Okay, that term, 0 squared, that's going to be minus 0. This term, 2 times 0, that's going to be minus 0. And this term is 2 over, it's minus 2 over lambda squared, 2 over lambda squared. And we have e to the minus lambda x, so e to the 0 power for x equals 0. That's just 1. So what we're left with now, we say that the integral 0 to infinity of x squared lambda e to the minus lambda x dx is equal to, so that's minus, that's 2 over lambda squared. Okay, so now our original thing we're going to do is we said we know from our integration by parts that this e of x squared is 2 over lambda squared. That's what we just solved for by applying integration by parts twice. And we have our e of x is 1 upon lambda. So it's 1 upon lambda, quantity squared is 1 over lambda squared. So you have 2 over lambda squared minus 1 over lambda squared using our variance equation that we had from before. That's just common denominator. 2 minus 1 is 1. So that's just 1 over lambda squared, which is the expression for the variance of an exponential random variable. Okay, and we get this by applying integration by parts and the variance equation. And for this integration by parts, we're doing it on this e of x squared term, and we're unwinding it twice by applying integration by parts 2 times. Okay, so with that, that's all I had for today, and we will end there. As usual, please make sure you're staying up with the reading and make sure you review these modules by Khan Academy. They are fantastically done. Integration by parts, first link, and indefinite and definite integral. All right, so with that, as usual, please stay healthy, stay safe, and I'll see you all on Thursday.